So they want us to graph this polynomial by hand. So why don't we first go off and find the x-intercepts. To find the x-intercept, you let y equal 0. We can then use the zero product property. So we have found the x-intercepts. Notice that I did ignore these powers for now. These will come into play when I draw the shape. For now, let me plot these points on the x-axis. So now that I have a visual, then and only then would I recommend that you go off and fill out a table of values. And what x's should you use? Well, pick points that are in between all of your roots. So things from here and pick some things from there. It is up to you to decide how many points you want to use. It's a matter of time. However much time you have, use it wisely. If you can only do a few points, that's fine. If you can do more, it's your decision. So the x-intercepts gave me a good idea of what x's to use. I went Casio calculator to get all of these crazy decimals. I plotted these points. Now, before I connect them, I'd like to revisit the original problem, and I'd like to establish a couple of things. First of all, what is the degree? The degree of this polynomial would be 1, 2, 3, 4, 5, 6. The degree is 6. So the arrows are either up, up, or down, down. Now, since a is positive, our arrows are going to be up, up. That lets me know that from here, the picture is going to go up toward the sky. Now, singles, doubles, and triples. At positive 4, I have a single. At negative 9, I have a double. And then at negative 1.5, I have a triple. These arrows, along with DT and S, singles, doubles, triples, that helps me to connect these dots. So I know this is going to go up. Now, it's a double root, so it sort of bounces off. And then it has to come up here and it has to grab these points. It has to grab those points. Now, I'm preparing for a triple root. So recall what triple roots look like. It sort of zigzags, right? It zigzags. Grab those points down there. Shoot back up. Single root goes up forever. So here they want the two roots that are imaginary. This polynomial has a degree of 6. Now, I have single, double, single, so that's 4. That means there are 2 that are not real, which I have to find. So the idea here is to go synthetic division. So go synthetic division with all these numbers. Okay, so drop in all the numbers first. There is a 1 right here. Now, we do have to feed it all of these values. So I can start with a negative 1, or I can start with this, or I can start with that, which, by the way, the coordinates here would be the conjugate of this. So let's just get that out of the way now. It does not matter which order you do this in, but make your life simple. Do the ones that are friendly. So I'm going to use negative 1. And you know what? Since it's a double root, I'm going to use it twice. Now I can throw in square root 5. And then I can throw in its conjugate. And then once you've done that, once you've fed it all of the roots that were given, then you can rebuild your polynomial where this is your remainder, this is your constant, this is x, and this is x squared. So we have x squared plus 0x plus 11 equals 0. You can dismiss this centerpiece. So we have x squared plus 11 equals 0. So x squared equals negative 11. And so x equals, if you square root, it's plus or minus. It's square root 11 because you can take away the negative, but you would have to put an I. And they were asking for the 2 imaginary roots. So give them what they want. Your imaginary roots would be square root 11i and negative square root 11i. Done. So let's run through a couple of exercises where I give you a degree and you tell me some of the characteristics about it. Let's pretend that the degree is 100. If my degree of a polynomial is 100, how many roots will there be? There are going to be exactly 100 roots. How many of the 100 can be x-intercepts? I can have at most 100 x-intercepts. Because think about it. I could have a picture that has 100 single roots. So I could have at most 100 x-intercepts, 100 single roots. How many complex roots? All 100. I could have 100 complex roots because the complex roots would be like 3i and negative 3i. They always come as pairs because they're conjugates. So you can have an even amount of them. And all 100 of them could in fact be complex. That could happen. There would be 50 pairs. There would be 50 couples, but there would be 100 roots in total. How many roots of multiplicity 6? So here's the explanation. So let me do a quick exercise here. So the degree is 100, but I want to know how many roots of multiplicity 6 I can squeeze into 100. So consider this example. X plus 1 to the 6th, x minus 1 to the 6th, x plus 7 to the 6th, etc. How many of these could I squeeze into 100? Well, here's the issue. Let's go 100 divided by 6, okay? And that says 16 and change. But I want to keep the whole part, 16. You see, I could have 16 building blocks like this because each one is worth 6. But if I have 16 of them, what's 16 times 6? 16 times 6 is 96. But the allowance, if you will, the allowance or the degree was 100. So I have 4 degrees left to spare with, but I cannot squeeze in another one of these because each of these is worth 6. So how many roots of multiplicity 6 could I have? 16. At most 16. So the fast way is take the degree divided by the multiplicity of whatever. And if there is a remainder, if there's some change, you throw away the change and you give me just the whole part. So let's try this again. But this time, instead of 100, let me change this to, let's say, 103. So if my degree is 103, I'm going to have 103 roots. All 103 could be x-intercepts. And for complex roots, since they come in pairs, I cannot have all 103 be complex because there would be an odd one. So I can have 102. I can have 102 complex and 1 extra one that's real, okay? And then how many roots of multiplicity 6? Squeeze in 17 roots of multiplicity 6. So for this one, you're given a picture, they want the equation. So to do that, you have to build it from scratch. So what I would do is I'd go through and go x equals all of my roots. So I have negative 3. I have this one here. Notice that they didn't put a dot. So you have to put a dot. And you know what that is because it's the conjugate of the square root 5. And they didn't put it on any of the other ones. So that's what that one has to be. So you have to do that with conjugates for things that are irrational and imaginary. And then we have also negative 1.75. We have 1. We have not this one because that's not a root. We have this one here. And then we also have a given root of 3i. I'll do it up here. So if 3i is the root, so also is its conjugate, negative 3i. Now let's build some of these factors. That one is just x plus 3 because you move this to the other side. This is an easy one. That's just x minus 1. This one here, let's work on this one. Turn negative 1.75 into an improper fraction. It's negative 7/4. Multiply by 4. Add the 7. So this piece is ready. What about these ones? Those, you could put those side by side. They would be x plus square root 5 times its conjugate, kind of messy, x minus square root 5. If you expand, it becomes x squared minus 5. That piece is ready. For these ones up here, those would become x minus 3i, x plus 3i. And if you expand it, you get x squared plus 9, because remember that I squared is negative 1. So let me put all these pieces side by side by side. Okay, so I believe I have all the pieces. But before we find A, you have to consider singles, doubles, and triples. So looking at the graph here, it looks like most of these are singles except this one. At 1, 0, it looks like we have a triple. So let me put a 3 now. Let me test this. The degree is 9. What's the degree of this? I have 1, 2, 2, 3, and 1. So that's 1 plus 2 is 3. 3 plus 2 is 5. 5 and 3 is 8. With 1 is 9. So all the singles, doubles, and triples have been respected. Now you can find A by taking this random point and plugging this in for x and plugging that in for y, otherwise known as h of x. And then divide. So A is 1 over 25. So final answer . And the directions would say things like your parenthesized factors can only have integers, and your A value has to be a reduced ratio, like a fraction instead of a decimal.